Let's take up extraction of crude metal from the concentrated ore. After the concentrated ore we have to extract the metal from it. So concentrated ore must be converted into such a form which is suitable for reduction. Usually sulphide ores are converted into oxides before reduction. Similarly, carbonate ores are also converted into oxide before reduction. And if we have hydrated oxides, then water is removed from hydrated oxide ore so as to get anhydrous ore for reduction. Why we convert carbonate and sulphide ores into oxides? Because it is easier to reduce oxide ore as compared to carbonate and sulphide ores. So thus the extraction of metals from oxide ores, first we have to convert the given ore into oxide, and then reduction of oxide to metal with a suitable reducing agent has to be done. Conversion to oxide, first is calcination. Calcination involves heating. When volatile matter escapes, leaving behind the metal oxide, carbonates also calcined so that they convert it into oxide and carbon dioxide is liberated. These are the example. Hydrated ferric oxide, when heated, we get Fe2O3 plus XH2O. Zinc carbonate, calamine, on heating gives ZnO plus CO2. Dolomite, CaCO3 into MgCO3 is heated to give CaO plus MgO plus 2CO2. These are the examples of calcination. Roasting. Roasting is applicable to sulphide ores, where sulphide ores are converted into oxides by heating in the presence of air in a furnace, but the temperature must be maintained below its melting point. So these are the examples of roasting. Zinc blendy on roasting gives zinc oxide plus sulfur dioxide. 2ZnS plus 3O2 gives you 2ZnO plus 2SO2. Galena, which is the ore of lead, is also roasted. 2PbS plus 3O2 gives 2PbO plus 2SO2. Cuprous sulphide, which is called copper glans or chalcopyrite, when heated in presence of oxygen, it will give cuprous oxide plus sulfur dioxide. 2Cu2S plus 3O2 gives you 2Cu2O plus 2SO2 are formed. This is a reverberatory furnace in which we carry out roasting. Here we have got magnesite lining, furnace charge, silica is used which can withstand high temperature. This is charge hopper in which ore is added. These are tie rod, hangers. This is also charge hopper from ore is added. So here we maintain high temperature so that sulphide ores get converted into oxide ore, and further their reduction can also be carried on. The sulphide ores or copper are heating in reverberatory furnace. If the ore contains iron, it is mixed with silica. Because ferrous oxide is a basic impurity, so we need acidic flux. Flux is a substance which reacts with gangue to form slag. So silica is acidic, which has to be added to remove FeO, which is a basic impurity. The iron oxide forms a slag, iron silicate, and copper is produced in the form of copper matte. Copper matte consists of Cu2S and Fes. FeO plus SiO2 gives FeSiO3. The sulfur dioxide formed in the roasting process is used for manufacture of sulfuric acid, which is most important chemical. Reduction of oxide into metal. Reduction of metal oxide usually involves heating some other substance, usually reducing agent, carbon or carbon monoxide, and even another metal can be used as reducing agent depending upon which metallic oxide we want to reduce. The reducing agent carbon can reduce the metal oxide, some of the metal oxide, not the all metal oxide. It will give metal and carbon monoxide will be formed. To understand the variation in the temperature requirement for the thermal reduction, this is called pyrometallurgy. Pyrometallurgy involves heating of ore so as that it gets converted into metal and oxygen is removed. And to predict which element will suit as a reducing agent for the given metal oxide, Gibbs energy interpretation are made, and these are called thermodynamic principle of metallurgy. Let's take up thermodynamic principle of metallurgy. The change in Gibbs energy delta G for any process specified temperature is described by the equation delta G is equal to delta H minus T delta S, which you must have studied in class 11th. This is called Gibbs-Helmholtz equation. Delta H is enthalpy change, delta S is entropy change, and delta G is free energy change. For any reaction to take place, delta G must be negative. then only reaction will be spontaneous. Delta G is also related with equilibrium constant. Delta G standard is equal to minus RT ln K. Ln is log to the base E. If you want log to the base 10, then it will become minus 2.303 RT log K, where K is equilibrium constant of the reactant product system at temperature T. When the value of delta G is negative in the equation, only then reaction will proceed. If delta G is positive, reaction will not take place. So we can very well calculate at what temperature reaction will take place and what temperature it will not take place. If delta S is positive, that is entropy is increasing on increasing temperature, the value of T delta S should increase. That is, delta H should be less than T delta S, so that negative part is more and delta G becomes negative. If the reactants and products of two reactions are put together in a system and the net delta G of two possible reactions is negative, the overall reaction will occur. These reactions are called coupled reaction. Means in one of the reaction delta G is positive, another reaction delta G is negative, and we add both the reactions to get delta G negative. It means both the reaction can take place simultaneously, and these are called coupled reaction. So the processes of interpretation involves coupling of the two reactions, and that will decide which reducing agent will be most suitable at a particular temperature. Such coupling is easily understood through Gibbs energy versus temperature plots for formation of the oxides. Application of these plots are in extraction of iron from its oxide in delta G versus temperature plot representing the reaction Fe to FeO, and plot goes upward, and that representing the change carbon to carbon monoxide goes downward. At a temperature above 1073 Kelvin approximately, carbon and carbon monoxide line comes below the FeO line. That is, delta G C to CO is less than delta G Fe to FO. So in this range, coke will be reducing agent and the FeO, and carbon itself will get oxidized to carbon monoxide. The reduction of Fe3O4 and Fe2O3 at relatively lower temperature by carbon monoxide can be explained on the basis of lower lying points of the intersection of their curves with carbon monoxide and carbon dioxide curve as shown in diagram. This is the diagram where we have plotted delta G versus temperature, and various plots are given where metal oxides are being formed and carbon is reacting with oxygen to form carbon monoxide, and where carbon is reacting with oxygen to form carbon dioxide. Their point of intersection will decide the temperature at which carbon monoxide are suitable reducing agent. This is the point of intersection where we can decide that magnesium will be able to reduce aluminum at what temperature. We find that this temperature is extremely high. That is why this method of reducing Al2O3 with magnesium is not economical. So from these diagrams, we can easily interpret that which reducing agent is most suitable for a particular reduction at a particular temperature, and which reduction will be economical in nature, because if temperature is low, it will be economical. If temperature is very high, it will be uneconomical. In blast furnace, reduction of iron oxides take place in the different temperature range. Hot air is blown from the bottom of the furnace and coke is burned to give temperature up to 2200 Kelvin in the lower portion itself. The burning of coke therefore supplies most of the heat required in the process. The carbon monoxide and heat moves to the upper part of the furnace. In the upper part, the temperature is lower and the Fe2O3 and Fe3O4 coming from the top are reduced in the steps to form FeO. Thus, the reduction reactions taking place in the lower temperature range and in higher temperature range depend upon the points of corresponding intersection of delta Ga standard of the reaction versus temperature plots. These reactions can be summarized as follows. This question has been asked in board exam. At 500 to 800 Kelvin, that is at lower temperature range, carbon monoxide will reduce ferric oxide to Fe3O4 plus CO2 is formed. Fe3O4 can be reduced with carbon monoxide to form 3Fe plus 4CO2 is formed. Fe2O3 is reduced with carbon monoxide to form 2FeO plus CO2. So these reactions are taking place at low temperature range. 900 to 1500 is the moderate or intermediate temperature range, or high temperature range also we can call it, but it's not very high. Carbon plus CO2 gives you 2 carbon monoxide. FeO reacts with CO to form iron and CO2. Limestone is decomposed to form calcium oxide plus carbon dioxide. Limestone gives calcium oxide, which acts as a flux, and it removes silica as an impurity in the form of calcium silicate, which is removed as slag. Slag formed is in molten state and is lighter than air, so it prevents the oxidation of iron and can be easily separated from the molten iron. This is the blast furnace where reactions are taking place. FeO reduced with carbon to form FeO plus carbon monoxide. Carbon reacts with oxygen to form carbon dioxide. Carbon reacts with CO2 to form 2 carbon monoxide. FeO reacts with carbon monoxide to form Fe plus CO2. Calcium oxide, which is obtained from limestone, reacts with silica to form calcium silicate, which is slag, can be easily removed. Limestone decomposes to form calcium oxide plus CO2. Fe3O4 gets reduced with carbon monoxide to form ferrous oxide plus CO2. Fe2O3 is reacting with carbon monoxide and reduced to Fe3O4 plus CO2. Exhaust gases are CO and CO2. The iron obtained from blast furnace contains about 5% carbon and many other impurities like sulphur, phosphorus, silicon, and manganese. This is known as pig iron and cast into variety of shape. Cast iron is different from pig iron and is made by melting pig iron with the scrap iron and coke using the hot air blast. It has less percentage of carbon and is extremely hard and brittle. Further reduction, wrought iron and malleable iron is the purest form of commercial iron and is prepared from cast iron by oxidizing impurities in reverberatory furnace lined with hematite. The hematite oxidizes excess of carbon to carbon monoxide, and we get purest form of iron called wrought iron, which is used for making iron beds and other malleable because it's malleable and ductile. Fe2O3 plus 3C will give you 2Fe plus 3CO. Limestone is added as flux, and sulphur, silicon, and phosphorus are oxidized to corresponding oxides. SO2 is removed, CO2 is removed, SiO2 is reacted with calcium oxide to form a slag. MnO also reacts with SiO2 to form Mn silicate, which is manganese silicate, which is also removed as slag. The metal is removed and freed from the slag by passing through the rollers. Next, we are taking extraction of copper from cuprous oxide. If you observe the graph plots between delta G and temperature, we will find that formation of oxide of cuprous oxide is almost at the top. So it's quite easy to reduce oxides of ores of copper directly to the metal by heating it with coke. Or we can also heat it with carbon monoxide. So both the lines of carbon, carbon monoxide, carbon and carbon dioxide are at much lower position in the graph, particularly in the range of 500 to 600 Kelvin. However, most of the ores are sulphides and some may also contain iron. So sulphide ores are roasted, smelted to give oxide. 2Cu2S plus 3O2 gives you 2Cu2O plus 2SO2. The oxide can then easily be reduced to metallic copper using coke. Cuprous oxide plus coke gives 2Cu plus carbon monoxide. In actual process, the ore is heated in the reverberatory furnace after mixing it with silica. In the furnace, iron oxide, which is basic in nature, reacts with acidic flux, that is silica, to form iron silicate, which is removed as a slag. This is the reaction which is taking place. And copper matte contains Cu2S and FeS. Copper matte is then charged into silica-lined converter, where silica is also added and hot air blast is blown to convert remaining FeS to FeO and Cu2S to Cu2O and finally to metallic copper. The following reaction takes place: 2FeS plus 3O2 gives you 2FeO plus 2SO2. FeO plus SiO2 gives you FeSiO3. 2Cu2S plus 3O2 gives you 2Cu2O plus 2SO2. 2Cu2O plus Cu2S gives 6 copper plus sulfur dioxide. This copper obtained is called blister copper because it has blisters due to sulfur dioxide. that is spots due to sulfur dioxide. This impure form of copper can be converted into pure form by electrolytic refining. Extraction of zinc from zinc oxide. The reduction of zinc oxide is done using coke. The temperature in this case is higher than that the case of copper because zinc is more reactive than copper. For the purpose of heating, the oxide is made into briquettes with coke and clay. Zinc oxide reacts with coke at 673 Kelvin to give zinc plus carbon monoxide. The metal is distilled off and collected by rapid chilling. So zinc can also be purified by electrolytic refining as well as distillation.